Okay, so okay, so
okay, I'm audible to you guys.
There's still an echo.
I'm audible to you.
Oh, yes, it's better now.
Okay, so I had kept audio on both this thing. Okay. Okay, so the first part which you see here, which is basically they have given that the function f and its derivative both are continuous for all the values of x in the domain a to b. I mean, and in the domain that they have specified, and you have to find out the values of a and b. Now, this becomes one of the favorite question because it tests your concept of functions and calculus both. Now, as I told you, like for the continuity, if the function is continuous, you just plug in x as 2 here. Okay, so now when you say x is 2, like, so look, this function is valid for less than or equals to 2, and this is valid for x greater than 2. Now, ideally, when you're testing for the continuity, like you're testing around the limit concept, right? As x tends to 2 positive function, and is it equals to limit x tend f of x x tending to 2 negative. So when I say 2 positive, I'm going to take this function because this is valid for higher than or equals to 2. So that's going to be 2 times 2 minus 1, which is 4 minus 1. That's 3. And when you look at the second function, which is here, now this is where it is valid for x, sorry, this is x less than or equals to 2. This one is valid for x less than or equals to 2. So I'm just going to take for that function, it will be 2 times 2 minus 1, which is 4 minus 1, which is 3. And so in this case, what you see is that x less than 2, less than or equals to 2, this function is valid, and x greater than or equals to greater than 2, this function is valid. So now when you take the limit for x greater than 2, so that's this function, which is limit f of x tending to 2 positive, I'm going to take this function. So here what you see is that it's going to be a times 2 squared plus b times 2 minus 5. That's a 4a plus 2b minus 5. And this is equals to 3 basically, because they both need to have the same y values around the point of discontinuity. So when you look at this, you basically get 4a plus 2b minus 5, 4a plus 2b minus 5 equals to 3. So you get first equation, which is 4a plus 2b, which is nothing but 8. So you got this one equation. Now, second is the derivative is also continuous. So what we do is, the function is differentiable here. So in this case, what we do is you do the derivative around both the left limit and right limit. So if I do derivative, my f dash x is basically this is 2, and this is 2ax plus b. That's the derivative of this part. Derivative of this constant will be obviously 0. Now this is valid for x less than 2, and this is valid for x between 2 and 3. So now since this is also a continuous, differentiable function. So what we do is you plug in x as 2 here, which is obviously 2 itself, and you plug in x as 2. So my left-hand derivative limit x tending to 2 positive for the function derivative will be, if I say x less than 2, x greater than 2 will be, you plug in 2 here, so will be 2 times x, which is 2a times 2 plus b, which is 4a plus b, and my left hand limit is limit x tending to 2 minus, it is basically 2. Now these two should be the same, so that's why 4a plus b equals to 2. So now you got two equations, this and this, so you solve them. So 4a plus b equals to 2. So if you subtract them, if I take this minus, so you get b equals to 6 basically. Now once you plug in b as 6 in any of the equation here, if I plug in, I get 4a plus 6 equals to 2. So that gives us 4a equals to minus 4, and this gives us a is minus 1. So by this way, we can find out the values of A and B using the concept of continuity and differentiability. So the moral story is here, basically, if you take left and right limits and all those, if it is confusing you, just simply just write down the x values. Once you put the x as 2 here, you don't need to write down all of these stuff in that case. If for function continuity, you plug in x as 2 here, you equate both the values, which at the end we get this. You plug in x as 2 and x as 2 in their derivatives, which we have done here, and that gives us this equation. You solve them, and you get the value of b, you get the value of a. Now, this is basically, you can see that is the function. Now, do we have to actually graph to see this particular part, whether it is 1-to-1, if it makes sense? So in this case, what we have is the given function is 2x minus 1, which is for x less than or equals to 2. And this is the second function. Now, it makes a lot of sense if we graph this. So if I take, let's say, 2 here, since this function is valid for x less than or equals to 2, if I plug in x as 2 here, I get the y value is 3, and it cuts, a straight line is like here, it cuts at -1. So that's your first function. And the second function is with the quadratic, which is a is -1, so negative x squared plus 6x minus 5. Now this is a quadratic. Now let us just try to find out the vertex for this. So if I plug in x as minus b over 2a here, if you do that, you get minus of 6 over 2 times minus 1. That gives us x as 3. So x as 3 here is basically x as 2 actually here, minus b over 2 times a. That gives us x as 3. Yeah, sorry. So x coordinate is 3. So the vertex is at x equals to 3 here. Now to get the y coordinate, you plug in x as 3 here. So you get negative 3 squared plus 6 times 3 and minus 5. So what we get is negative 9 plus 18 minus 5. So 18 minus 9 is basically 9. So 9 minus 5 is 4. So you get the y value at this function. The vertex is at 4. It's a sad phase graph. So it's continuous function. So it has to join with this 3. So this is the function, obviously, and now it clearly shows it is 1-to-1 function. For a reason being, it is purely increasing function. Purely increasing, you can see the slope is always positive. Or you can say it passes the horizontal line test. Since you draw a horizontal line, it cuts the graph at only one point. Hence, it is basically the 1-to-1 function. And the next part they're asking is write down an expression for the inverse of this function. Now look, inverting the function is always about, for hybrid function, you got to be very careful. So you find out the inverse of individual functions first. So if I find the inverse of the y equals to, let's say, 2x minus 1, you'll get like x plus 1 over 2 as the inverse. And second one is a quadratic. And obviously you need to have the perfect square for that. Since we already know the vertex and we know the coefficient of x squared, it makes our life easier. So the coordinate of coefficient x squared is -1, so it is negative x minus 3 the whole square plus 4. That's the using the vertex form. Now you just find out the inverse. So find interchange x with y. So you get x equals to y minus 3 the whole square plus 4. So you get from here, you get x minus 4 over -1 equals to y minus 3 the whole square. So y minus 3 equals to plus or minus a root of 4 minus x. And then you get y is 3 plus or minus root of 4 minus x. And out of this, I'm going to take -1 because it is, I have retained the left side of vertex. So my final expression for inverse in this case will be f inverse x will be 3 minus root of 4 minus x. Now, what is very important is that now, so this is the first half. The second half is 3 minus root 4 minus x. Now, domain for this function, original function, as we know, becomes range for its inverse. So the range of the function, which was y less than 3, becomes the domain, which is x less than or equals to 3. The range of this original function was between 3 and 4. so that becomes a domain. So between 3 and 4, so that becomes a domain for its inverse. So this is very, very important question that you need to be careful about, where your function tricks, your calculus skills, all of them come very, very handy. So more or less, when you look at the maxima minima, obviously you need to be very careful with the single derivative and double derivative. Now, when obviously like this is just a recollection process, I'm not going to do in detail. I'm just going to write down the procedure. So you remember that first you're going to find that f dash x equate to 0, solve for x. Once you solve for x, then you have got 2 ways to verify. Either you draw sine diagram for single derivative, or you draw, you find out the second derivative. So if you find second derivative, so I'll just first complete this part. So sine diagram, if it is changing from positive to negative, okay, this is a derivative sine diagram. It is obviously increasing and then decreasing. It's a maximum. And if it changes from negative to positive, it's like a minimum. So what is really important is that what if it doesn't change? So if it is positive, it means that it is increasing, but at some point, so it's increasing and some point its derivative is 0 and then again increasing. So this is referred as non-stationary point of inflection. So sometimes it's not always, wherever the function is purely increasing, that your derivative is also 0 in between. In that case, there is a possibility that you can have a stationary point of inflection. So this is a possibility that you can have here a stationary point of inflection. So if sine diagram is a positive or negative around that point, like suppose the graph is like this or something, or you can see the slope is negative, here also negative. So it is a possible non-stationary point of stationary point of inflection. Now, what you could do is you could verify the maxima minima with the second derivative sine diagram as well. So after solving for x, let's say I got certain values, x as a or x as b, you plug in the second derivative function. If second derivative is also positive, it means that's a concave up function, which is going to be a minima, because double derivative tells your concavity. So if the function is concave up, your double derivative will be negative, I mean positive. If your second derivative is negative around any of the points, then it is like a concave down. So a question can be that, okay, what if the second derivative is, let's say, coming to 0? In that case, this is a possible point of inflection. So I'll just touch base upon that in a bit. So for point of inflection, you straight away equate second derivative to 0. So equate second derivative to 0. You solve for x. To verify, so this is necessary criteria, but not the sufficient. So you verify, so you do the second derivative or sine diagram. So if you draw the second derivative sine diagram, it is, let's say here, it is, let's say, positive and negative. It means this side is concave up and then it is becoming concave down. So this is a possibility of the point of inflection. This confirms indeed point of inflection if you have equated second derivative to 0. But to, like, there is certain confusion that goes in students' mind, is like, okay, what is a point of inflection basically when in terms of, let's say, stationary point. So after you solve for x, let's say, you can just substitute this in single derivative also. You can plug in this x coordinate in single derivative. Now, if single derivative is also 0, that means that it is a stationary point of inflection. So it is a stationary point of inflection, because if for any point of inflection where your single derivative and double derivative both are 0, then they are stationary point of inflection, provided sine diagram is verified. Okay, so here the first few parts are obviously pretty decent and easy. Now the concept is that, okay, you have been given a function which is f of x is ln x upon x. and you have to solve for derivative equate to 0. So in this case, obviously you can see here that it's you apply quotient rule. I have done already to save time. So x times 1 by x. So v square vu dash minus uv dash. So that becomes 1 minus ln x upon x square. Obviously, when you solve for x, it is 1 minus ln x equals to 0. So you get ln x is 1, and then you get x as e. Now, the next is to verify whether it's a local maximum or not. So obviously, either you have got two ways now to do it. So number one is you can either draw the sign diagram of single derivative, or you can actually find out the second derivative. So I have found out the second derivative here. So you can see that second derivative, for me, this denominator is like your u, and entire numerator is, denominator is v, and entire numerator is u. So you do v square vu dash minus uv dash. So obviously, if you take x common from here, if you open the brackets and take x common, one of the x can get cancelled, and you get second derivatives minus 3 plus 2 ln x upon x cubed. Now you're going to input this x coordinate that we had got from the previous part here into the in place of this x. So you get negative 3 plus 2 ln x, 2 ln e upon e cube. Will be negative 3 plus 2 upon e cube, which is obviously negative 1 upon e cube. Since now the second derivative is coming as negative, if it's less than 0, it obviously this has to be a local maximum. So that's the validity for the first part. Then they're asking, okay, write down the range of this function. Now, since this is a local maximum, there is this is the turning point. And so what we do is between 0 and e square itself. So what we do is you plug in x as e here. So it'll be ln e over e, which is 1 upon e. So this is the maximum y value. So the range of the function, since it's a log function, you know that log function have got the range as all real numbers. But since there is in denominator also you got an x, so you got to be very careful about the horizontal asymptote also. So as x tends to infinity, you will notice that ln x is going to grow at slower rate than x. Okay, so it is going to have a horizontal asymptote. So if I roughly sketch this graph, okay, so I'm not like, I don't have enough information, but if you see ln x, if I find out the root, ln x upon x equate to 0, if I do, I get ln x as 1, ln x as 0, so you get x as e to the power 0, which is 1. So since this coordinate is 1 here, this is the point where it crosses. And then there's a vertical asymptote at 0. And so in this case, the graph is going to be something like here, and it is going to have a turning point at E. So turning point at E, and this Y value is 1 by E. So you can see that this is basically the range is like Y less than or equals to 1 by E, Y less than or equals to 1 by E. But more important is like, how does this side of the graph approach? So since as ln x and x, if you compare, now when ln x value, for example, if you look at, like, if I find out ln 1000, ln 1000 is like a numerical number, single digit numerical number or something, or let's say 2-digit number. But as x is 1000, it is obviously much bigger than, like, you know, ln 1000. So what happened is that slowly, as the function initially grows faster, because ln x is growing faster than e, but after that, it's like, you know, slows down and there is a horizontal asymptote. So that's the first, second, and third part. For third part, fourth, I mean the B part, we have to find the point of inflection and determine its nature. So for, as we discussed just now, that this for point of inflection, equate second derivative to 0, solve for x, and then verify with the sign diagram of second derivative. So I'm just going to equate the second derivative to 0. If I equate the second derivative to 0, what do we get is basically, if I equate second derivative to 0, so you can see that I get the function as negative 3 plus 2 ln x upon x cubed, which is nothing but ln x equals to 3 over 2. So x is e to the power 3 over 2. So there is basically a point of inflection as x equals to e to the power 3 over 2. So that's the x coordinate. Obviously, if you plug in this x coordinate in the function, you will get the y coordinate as well. So that was about the point of inflection. And obviously to verify, you'll have to draw the sign diagram of second derivative, which is obviously a little tricky, but they did not ask us to verify it. So you don't need to do it at this stage. Yet we have to sketch the graphs clearly indicating the asymptote, x-intercept, and local maximum or minimum. Since we just found all the information, or we got the one as the root e and 1 comma e is the maximum, e to the power 3 by 2 is the point of inflection. So you can clearly see that before the point of inflection here, the graph was concave down. You can see clearly, and after that it becomes concave up, and it approaches to x-axis. So this is the meaning of the non-stationary point of inflection. So non-stationary point of inflection. So this is the graphing part, and let's move to the next part now. Okay, so the next part is we have got ln x. We have to sketch the graph of ln of absolute value of x over x, and second part is ln of absolute value of x over absolute value of x, and then you have to solve where is h of x greater than g of x. Now this is interesting because we just sketch the graph of f of x, which is here. So f of x graph is something like this. There is a turning point, then there is a point of inflection here, and this point is 1 comma e. Now what is interesting is that this function is not like completely the f of absolute value of x function. This is the absolute f of absolute value. So sketching h of x is pretty easy. Just reminding you, how do we sketch f of absolute value of x? So suppose if you got certain part of the graph, irrespective of this question, you're going to cut down the left side of the graph and reflect the remaining part across y-axis. So reflect the remaining part across y-axis. That's your f of absolute value of the x graph. And now what we have is okay, so in this question, you don't see any negative side. So you just have to reflect this remaining part in y-axis. So that's the graph of this. Along with this is the graph of f of absolute value x. So this is the graph of this h of x. And for this, obviously, you can see that, I mean, since they haven't asked the range of g, so I'm not going to do that first. Now, range of h. Now, for this one, we sketch the graph. Now, only difference that you notice is that this side x is positive and ln absolute value. So this side is not going to be any different. The only thing is that this side. Now, this side, you can see that since x is being left as it is with its sign, the numerical value of the ratio is going to be the same. Like, for example, here I take x as, let's say, 2. Now I'm going to do ln of absolute value of 2 upon 2, which is, you can see that it is same as ln 2 upon 2, which is same as original function. That's why this side of the graph is remaining as it is. But in the left hand side, now you notice that if I put ln of absolute value -2 over -2, now it is ln of 2 divided by -2. So the only thing that you notice is it's a negative of the exact same value. So it means that your graph now, this part will be just reflected in x-axis. So here, if I wish to sketch the graph, this side it is going to be something like this, and this side it remains as it is. So here it remains as it is. So now for the range of g, if you notice here, range of g, if I look at in this function, you can see clearly that this side it is obviously like, you know, greater than 1 by -1 by e, but this side it is all the way going down. So basically it is all real numbers. You can clearly see this is all real numbers. So a lot of times, you know, you find these things difficult because you have like, you know, no idea how to tackle the graphing part, how to understand the graphing part. So last of the value that we have, last of the part of the function we have is h of x is greater than g of x. Now my h of x function is the original function that you can see is this function here, and g of x is the function which is in the green. So I have to find out where h of x is strictly greater than g of x. And you can clearly see that this is happening only between here until this point. And pardon, this is not extending all the way to the left because they have fixed up the limits here. So this is like until e squared. So this is not going all the way down as a horizontal asymptote. So this is just till e squared. So in this case, you can see that the part of the graph that is above the green function is only this particular part. You can see that clearly. So for that, my answer, you don't need to even find out the intersection, because you know they are going to intersect at this point is obviously like this was at 1. So this is going to be at -1. So this is going to be negative e squared. So that holds true only if I take x value from negative e squared until -1. So that's the correct range for the last value or last question, you can say. So here when you see the first thing that has been given is obviously this is the derivative graph and you want to sketch the original function. Using the ideas and the logic that we have learned, we are going to explore the possibility of like, creating a graph that fulfills the criteria of being f of 0 as 0. Now, f of 0 as 0, it means that it passes through origins. That's straight away an indicator for you to understand that. Now, remember that the graph has got a positive slope all the way until 3, apart from 1 being 0. Rest of the graph, remember, above the graph, you have got positive derivative, and below the graph, you have negative derivative. That indicates that the function has been thoroughly increasing until here, apart from this one. So the derivative, the rate at which the function is increasing. Now here it was slope was high positive, then it became slower and slower. So from a high positive slope, like, just coming all the way like a little slower, then here you get at 1, you can see there's sign diagram of single derivatives, both the sides above x-axis. So here you will have a possible point of inflection at 1, which is stationary point of inflection. And then again, it will shoot up. At 3, you notice that there is derivative changes from positive to negative. So the function which was positive, it became negative. It is positive at 3. So at 3, there is a turning point, and that's it. So if I pick up this graph, so this is at 3, and so this is at this is the maximum point. And after that, you can see here at 2, you can see there is a maximum of the derivative. Now, what interesting thing that 2 holds for us is that wherever you will notice that if the derivative function has got a maximum or minimum, that's the point you're going to have stationary or non-stationary points. So you can clearly see at 2, there is a non-stationary point of inflection. So this is a non-stationary point of inflection. So this is like, backward tracing. Understand that on y-axis you've got the derivative function. Understand that your slope is represented by here the y value directly. So like, don't try to look at slope of the slope, because then that will be the second derivative. So this is important. This is something that you need to understand, that on y-axis you have now the derivative. This is no more a y value. This is a derivative. So this is one of the questions that is asked like, several times in exam. So please be mindful of this. Okay, so here what you notice is that this is one of the questions that is engaging the tangents and normals concept, and also implicit differentiation. So remember that whenever you're differentiating a function y to the power n with respect to x, it is n times y to the power n minus 1 times dy by dx. So that's the derivative. So now remember, for tangent, so it's like an ideal scenario here where they have given, okay, there is a curve. Okay, so what they have given is that, okay, if I draw a tangent at any point, okay, so it cuts the x and y axis. At 1, it cuts at 0, n. Other one, it cuts at n, 0. And you have to show that it adds up to a. That's the y and x intercept add up to a. So this is x to the power half plus y to the power half, okay, equals to a to the power half curve. So first what I'm going to do is I'm going to just get the equation of this tangent. Okay, so equation of this tangent is obviously you find out your x coordinate is p here, y coordinate is q. So first we find out dy by dx. So x to the power half plus y to the power half equals to a to the power half. You're going to do the derivative of both sides. So you do the derivative here, you do the derivative here. You get derivative, this is 0 because it's a constant. And derivative of the side, which is obviously x to the power half is 1 over 2, x to the power negative half. And derivative of this y to the power half is plus y to the power half, y to the power negative half into dy by dx equate to 0. So what we get is, it basically, the derivative is 1 over 2 root x plus 1 over 2 root y equals times dy by dx equals to 0. Now you're going to bring it this thing here. So you get dy by dx is basically negative 1 over 2 root x, negative 1 over 2 root x times 2 root y, because if you multiply, you this what I get. You give this cancel, it's going to be negative root of y over x. Then I can condense them to a single square root, and you get negative here. Now, next part is, how do I find out the coordinate or slope at that point? So slope is going to be negative root p by q, negative root q by p, sorry. So that's your negative slope, I mean the slope of the tangent. So now your slope of tangent is negative root q by p times x and plus p. So this is until here. So now what do we do after this is, you're going to plug in x coordinate as p and y coordinate as q. So plug in q equals to negative root q by p times x is nothing but p plus c. So it'll become q minus, if you break this up, it'll become q equals to root q over root p, and I can write down this p as root p the whole square equals to I mean plus c. So one of the root cancels and you get here is negative, of course. So you get c equals to q plus root pq, because root q times root p is root pq, and minus, if I move to the other side, it becomes plus. So in short, we got the y-intercept, which is nothing but the value of m. And similarly, you have to get the x-intercept. So you got the equation, which is y equals to negative root q over root p times x plus q plus root pq. Now you plug in here y as 0 to get the x-intercept. So if I plug in y as 0, you get this will be 0 equals to, or you can say I move this thing here. So 0 plus this will be root q by root p is times x equals to q plus root pq. Now if you cross multiply this thing here, the x is going to be, actually when you solve for this, it is going to be root first you multiply here, so root q equals to q times root p, and root p times root p is going to become p, and here is root q left out, so root q, and then you divide by root q. So you will get the answer for x-intercept as q plus root, sorry, p plus root q, pq, p plus root pq, because if you divide by here, your one of the root q cancels, but there is one root still there, because this I can write down root q square. So if you divide it here, root q, then one of the root q get cancelled, and obviously you take it common, so this one also get cancelled, so you get p plus root pq. So this is the value of n in short. Now I'm going to add m and n both. So value of m is this, and value of n is this. So I'll just clear out everything here, indeed this part. So we have now m plus n will be q plus root pq and plus p plus root pq. So if I add p plus q, I get p plus q plus 2 root pq, which is root q. And if I take this as root p the whole square plus root q the whole square plus 2 root p root q, this is nothing but root p plus root q the whole square. which is nothing but if I plug x as root p here, y as root q, because it lies on the curve, I get that as a to the power half. So this is nothing but a to the power half whole to the power 2, which is nothing but a. That's how you can see m plus n equals to a in short here. Okay, so here we have been given a question that is obviously a rational function, and you have to find out the where it meets the coordinate axis, and then you have to find asymptotes, turning point, and sketch the graph. So first thing is that, let's say for roots, you equate the function to 0, you get x as 3. And for vertical asymptote, I mean y-intercept, you plug in x as 0. So if I plug x as 0, I get 9 over 2. So 9 over 2 is the y-intercept. And for the asymptotes, you get x as 2 vertical asymptote. Here there is no horizontal asymptote, you have oblique asymptote as the degree of numerator is higher than degree of denominator. So you're going to basically do, first you open this up, it gets x squared minus 6x plus 9 divided by 2 minus x. So we have to find out the, let's say, oblique asymptote here. So you do the long division. So you've got negative x plus 2 here, and you're dividing x squared minus 6x plus 9. You take negative x here, so it gets negative positive x squared, and negative 2x. This is minus, this become plus, cancels, you get negative 4x and negative 4x plus 9. So you take positive 4 here, so it become negative 4x plus 8. So it become positive. When you subtract, this is 1. So I can basically rewrite this function as negative x plus 4 plus 1 over 2 minus x. Now basically it's like your quotient plus remainder over divided. So that's your function. Now, as you know that oblique asymptote is the quotient itself. So y is negative x plus 4, that's your quotient. Y is negative x plus 4. So that's your oblique asymptote as well. Now you have to find out the turning point. Now for turning point, you can use calculus or you can use discriminant. I know calculus method is easy, so I'm not going to do that. If you're doing calculus method, you just have to open up the bracket, do the derivative, or you apply chain rule, quotient rule and all, and get the derivative and equate to 0 and solve for x. So now for discriminant method, you have got, let's say y is x squared minus 6x plus 9 over 2 minus x. You cross multiply it here, so you get 2y minus 2x is equals to x squared minus 6x plus 9. Bringing everything one side, so x squared minus 6x. This is minus, not 2y, minus, it is 2y minus xy, sorry. This is xy. So you bring in the x terms will become x squared minus 6x plus xy and plus 9 minus 2y equate to 0. So I'll get x squared minus or plus, if I take x common, so it is y minus 6 times x plus 9 minus 2y equals to 0. So 9 minus 2y, yes. So now you do b square minus 4ac greater than or equals to 0. So y minus 6 the whole square minus 4 times 9 minus 2y greater than or equals to 0. You open up the bracket, you get y square minus 12y plus 36 minus 36, and then you get plus 8y greater than or equals to 0. Cancel. You get y squared minus 4y greater than or equals to 0. So you get, if you draw the sign diagram, you get 0 and 4. For this, it's negative here, and positive here, because it's a happy phase graph. So you're in this function, your y is greater than or equals to 4, or y is less than or equals to 0. So this is the y value. And now if you plug in this y as 4 in this and solve for x, you will get, or you can just plug in y as 4 here. If I plug in y as 4, I get x squared plus 4 minus 6 is -2, so -2x, and plug in 4, so it'll become 9 minus 8, which is plus 1 equals to 0. So you get the root for this as x equals to 1. So you get x as 1 here if you factorize. So your this point is 1 comma 4, and similarly plug in y as 0. So if I plug in y as 0, I get x squared minus 6x plus 9, which gives us x as positive. X squared minus 6x plus 9 equals to 0. You get x as positive 3. So this is the turning point. So 1 comma 4 and 3 comma 0 comma 3 comma 0 is the turning point. Now you just sketch the graph with the given information. So you take out the critical information from each subparts. So here you got an oblique asymptote first. We draw that, which is 4 minus x. So it is something here. It's a negative sloping line cutting at y-axis at 4. Then there is a turning vertical asymptote at x equals to 2. And then there is a root at x equals to 3. So here. And then there is a turning point at 3 comma 0. Okay, so this side it will be like here. This side will be here. And then this side, your y-intercept is 9 by 2. So this will be something like this in this case, parallel to the oblique asymptote. This is how you do some of the main critical things about such question. Okay, so this is one other question, obviously on integration that you can see involving partial fraction. And first thing you notice here is that there is a square term here and square term here. And remember that you can do partial fraction only where you got a degree of numerator is lower than degree of denominator. So in this case, I'm just going to do one thing is I'm just going to add up one more step. And so this is, if you open this up, denominator will be x squared plus 4x plus 3. And so if you divide here, you get x squared plus 4x plus 3. If you subtract, you get negative x. So this can be written as quotient plus remainder over divided, which is x plus 1 and x plus 3. Now you have to do partial fraction on this. So if I do partial fraction on x upon x plus 1, x plus 3, this is going to be a over x plus 1 plus b over x plus 3. So x is going to be a times x plus 3 plus b times x plus 1 when you cross multiply this out here. Now take x as, let's say, -1 both the sides. So you get -1 equals to a times -1 plus 3, and this becomes 0. So a equals to -1 by 2. And once you get x is -1, similarly plug in x as -3. So you plug in x as -3 here, you get -3 equals to b times -3 plus 1, because this becomes 0 anyway. So -3 equals to b times -2. And this b you get as 3 over 2. So when you open this bracket, basically plug in the values of the a and b constant and you replace out here. Remember that you've done partial fraction on this, so this minus is still significant. So you have to put that here, put the values of a and b. If you open it up, this is what you get. Now I have to show that the integral of the function from 0 to 3 is this. So obviously you've got to integrate this, which is 1 integration plus 2x plus 1 minus 3 by 2x plus 3. So integration of 1 is x. This integration is 1 upon 2 ln x plus 1 minus 3 over 2 ln x plus 3. So now you put the limits, let's say 0 to 3. You plug in 3 here, so you get 3 plus half ln 4 minus 3 by 2 ln 3 plus 3 is 6. So that's your one stuff. Now you put it x as 0. So minus 0 will be 0, half ln 0. This will be half ln 1, which is again 0. And this will be minus 3 by 2 ln 3. So minus 3 by 2 ln 3, that's the value of this expression. So this becomes plus actually. So it'll become plus 3 by 2 ln 3. So you get the answer as 3 plus half ln 4. Now half ln 4 is nothing but ln 2 square. If you bring it down, it becomes 2 upon 2, which is simply ln 2. And minus 3 by 2 ln 6 plus 3 by 2 ln 3. Now if you simplify this, 3 by 3 take common. So what do we get is basically, I'll just erase this part here. So 3 by 2, we get 3 by 2, sorry, this is 3. This is not 3 by 2. So this is 3 plus ln 2 plus 3 by 2 you take common. So it becomes ln 3 minus ln 6, which is 2 plus ln 2 plus 3 by 2 and ln half. This is going to become 3 by 6, which is ln half. And ln half is nothing but negative ln 2. Because if you take 2 up in the power, it'll become ln 2 raised to negative 1 and negative can be brought down. So basically this expression finally it is 3 plus ln 2, so 3 plus ln 2 plus, minus 3 by 2 ln 2. So ln 2 minus 3 by 2 ln 2 is negative half ln 2. So it is 3 minus half ln 2. So this is an important question and you need to remember this.